Hey everyone, I just want to offer a few comments before going into lesson 9-8. And of course, before you go into lesson 9-8, you should work through partner quiz 9-7. That's the first assignment for this week. But I don't really have any comments about that, about the partner quiz. I know what you're all interested in is what are we going to do now that we're not going back to school for the rest of the semester? I'm interested in getting answers to that question too. And quite frankly, I don't have answers at this point. What I can tell you is that I will be updating the calendar for the rest of this semester to reflect what material we're going to be studying. And what I haven't figured out yet is what sort of work I will assign that is to be graded, or even how I'm going to grade that work. I plan to have answers to those questions by the end of the week and the new calendar printed, but I'm still working on that. It's a very, those are very tough questions for me to figure out, and I'm probably going to need some help from other people in my department. So anyway, that information's coming. Stay tuned. Let's now get into lesson 9-8, which is on the standard form equations of hyperbolas. Let me just make sure that the camera is seeing what we need it to see, and it's not yet. So there we go. That's better. Now we can see everything we want to see. All right, so this is not the notes for 9-8. This is a partner, not a quiz 9-5, but it's got these standard form equations for ellipses up there. And I just wanted to take a minute to look at these before we look at the standard form equations for hyperbolas, so we can compare and contrast those sets of equations. First of all, this is not how I, Mr. Nortillo, usually like to write these equations of ellipses. Instead of a squared and b squared, I like to call the denominator under the x term x radius squared, and the denominator under the y term y radius squared. And I would call them the same thing here, x radius squared and y radius squared. And so for me, you don't really need two different forms. I mean, why do people have two different forms and call this A and B, and then switch them around and call this B and A? I don't even want to waste time explaining why it's like that in so many math books and in so many online websites. I think it just gets confusing. Just know that whatever is under the x term is the radius in the x direction, which might be larger than the radius in the y direction, like in this case. Or it might be smaller than the radius in the y direction, like in this case. So in this case, what's being called a squared here for this ellipse would be larger than the b squared, because the radius in the x is larger. But for this ellipse, okay, since the radius in the x direction is smaller, then this number would be smaller than that number. It doesn't matter whether you call them a or b, right? But there's a plus between them, and of course the order of adding doesn't really make any difference. We could write the y term first instead of the x term. That really wouldn't change anything at all about the relationship between the graph and the equation. Okay, now here is the standard form equation for hyperbolas. It's got a minus between the terms. One term is positive and then minus the other, or you can think of this second term as the negative term because of the subtraction in front of it, right? Think of it as plus a negative y minus k squared over slope y squared. And the order of subtraction matters, right? Here it's x minus y, and here it's y minus x. And so the difference in the order of subtraction determines which way the branches of the hyperbola are going to open. You recall from first and second year algebra, we talk about the direction that a parabola opens. Does it open up or does it open down, right? Well, hyperbola branches sometimes open up and down. They look like back-to-back parabolas, and sometimes they open left and right. Okay? Well, if the leading term, the positive term of this equation is x, then the branches of the hyperbola will open in the x direction, left and right. And if the leading term, or the positive term, is y, then the branches will open in the y direction, up and down. Okay? We'll see that in two examples here. We'll get to this first example in a minute, but also notice that these denominators, I'm calling them something different because they represent something different. No longer do they represent a radius in any direction, but these two values are components of the slopes of the asymptotes. Whatever these numbers are, the square roots of those numbers, see, this is slope x squared and this is just slope x. So whatever that number is, let's say it's 25, the square root of that number, 5, would be one component of the slope value of the asymptotes. Okay? And so whatever denominator's under the x, that value is going to go in the denominator of the slope. Whatever is under the y is going to go in the numerator, because slope is always change in y over change in x, right? Always, always. Slope is y over x, rise over run. So it would be this number over that number, but in this case, it would be this number over that number, always the y over the x, okay? And I got a plus minus here just because there are always two asymptotes, one with a positive slope, one with a negative slope. It's not because of square rooting anything and getting a plus or minus. It has nothing to do with the minus here or any plus signs anywhere else. It has nothing to do with, the form of the equation or the signs in the equation. It's just because there's always two different asymptotes with two different slopes that happen to be exact opposites of each other. Okay? We'll come back to this equation in a minute. Let's skip down that and go right to the first example, where we want to graph the hyperbola that corresponds to this equation. Okay? So first, find the center. And again, there's no minus signs here. This is x minus nothing, y minus nothing. So the center is going to be at 0, 0. That's easy. Now the slopes of the asymptotes, take the square root of this number, 4. Square root of this number, 2. Now the slopes are either going to be plus or minus 4 over 2 or 2 over 4. Which is it? Well, the 4 came from x and the 2 came from the y. And slope is always y over x. So it's going to be 2 over 4, not 4 over 2. So here's the slopes of the asymptotes. Of course, that reduces to 1/2. So the asymptotes always go through the center, which is why the very first thing you want to do is find the center, and then from the center, up 1 over 2, up 1 over 2, up 1 over 2. There's one asymptote, down 1 over 2, down 1 over 2. And there's the other asymptote. Okay? So we found the center, we found the slopes of the asymptotes, we graph the asymptotes. Now we want to plot the vertices precisely. Okay, and again, if the x term is positive, the branches are going to open left and right. The branches are going to be out here somewhere, which means the vertices are going to be out here somewhere. Vertices are points on the branches of the hyperbola. They have to be to the left and right of center. The question is, how far to the left and right of center? Well, conveniently, the vertices will always be, again, exactly the square root of that number to the left and right, or, away from the center of the hyperbola. So the denominator of that leading term really is an answer to two questions. It's an answer to what's part of the slope value of the asymptotes, and it's also an answer to how far away are the vertices from the center of the hyperbola. Take the square root of that leading denominator, and that will tell you how far away the vertices are. So 1, 2, 3, 4, 1, 2, 3, 4. We've plotted the vertices. Now we can sketch the branches. Again, I remind you to draw good-looking branches. They should look like they are approaching the asymptotes all the time, getting closer and closer. Don't draw it like this, where it looks like it's getting farther away from the asymptote now. Also, don't make it look like, I don't know, don't make it look like a W, right? Don't make the branch look like a W. Make it look like like a U, more like a U, not like a W. Don't start by moving almost towards the center of the hyperbola. Don't do that, okay? And don't look like you're going to spear that branch right through the asymptote either. Okay, now that's all there is to graphing this hyperbola. But on a quiz or a test, I would likely also ask you to find the foci. Where are they exactly? Okay, now before I explain this work here, let me just remind you, when it comes to graphing ellipses and hyperbolas, first of all, again, with a plus in between, that's the dead giveaway. This has got to be an ellipse. With a minus, it's got to be a hyperbola. When you graph an ellipse, the ellipse goes around the foci, right? The center of the ellipse would be somewhere around here, and the foci are inside the ellipse. The foci are closer to the center than the vertices are, which are going to be out here somewhere, right? Whereas when we got a minus in the equation and we're drawing a hyperbola, the branches come closer to the center of the hyperbola than the foci are. The branches come in between the foci. They don't go around them. Okay? So with that reminder, let's realize here that once we've drawn the branches and plotted the vertices, a focus of this hyperbola is going to be farther away from the center than this vertex. And that visual reminder there helps us remember that that distance, which is related to these two values also in that Pythagorean type of way, that distance is the largest of these three. Okay? That's one of the distances squared, that's one of the other values squared, and then that is the third one, and that's the largest. So that's why in this equation is laid out this way. Distance to a focus squared is always equal to the sum of these other two numbers squared. Okay? One other difference between ellipses and hyperbolas, which makes hyperbolas, I think, a little harder to work through, is that in an ellipse, excuse me, that's not the picture I wanted to show you. In an ellipse, here's the picture of the ellipse I wanted. Those three distances that are related to each other in that Pythagorean way, they're all visually very well represented in the picture of an ellipse. One distance is from the center to a focus, which is going to be somewhere in there. The other distance from the center to a vertex, right there, farthest point away from the center. And the other distance is from the center to a co-vertex. So all those three distances are strongly visually represented in this picture. Whereas with the hyperbola, really only two of the three distances are clearly represented. One distance from the center to a focus, the other distance from the center to a vertex. There is no such thing as a co-vertex on a hyperbola. So where is that other distance? I mean, and if we were going to draw it from the center, I suppose we would go in this direction to draw it because the other two distances go. But like, where would it stop? It's not clear. It's not obvious at all. I mean, I could give an answer, but I don't think it would be very satisfying or memorable. Okay, so you just got to work at knowing, just knowing. This is one of the things that I think you have to kind of just memorize. Okay, that the f squared is going to be equal to the sums of these two squared numbers here. So 16 plus 4 equals f squared. There's that equation. F is 4.5. So if we go 4.5 units to the right and left of the origin, we'll find the coordinates of the foci. Okay. I got to remember to talk about this before I finish this lesson too. I'm just making myself a mental note there. Here's the second example. This time the y term is positive. Okay, so the branches are going to open up and down, and the vertices are going to be up and down. Okay, but first find the center. -2, +4. So there's the center. -2, +4. Slopes of the asymptotes. Square root of that is 3. Square root of that is 5. Should it be 3 over 5 or 5 over 3? Well, the y term produced the 3. So 3 goes in the numerator. Okay? And the x term produced the 5. That goes in the denominator. So 3/5 for the asymptotes. From the center, up 3 over 5, draw an asymptote. And then from the center, down 3 over 5, draw an asymptote. Okay? Now, the vertices. Again, always the positive term. Square root of that is 3. So from the center, go up 1, 2, 3, vertex. Go down 1, 2, 3, vertex. Now you can sketch the branches. Going through those vertices produces a very good picture. And we're done graphing the hyperbola. But again, if I asked you to find where are the foci now, got to remember f squared is equal to this squared plus this squared. You know, if as long as you remember that these two numbers are involved. Well, no, I was going to say something that turns out to be not correct. So let's just pretend I didn't start that sentence, okay? F squared is equal to this plus this. So 25 plus 9 is f squared. F turns out to be 5.8. So from -2, +4, we got to go up 5.8 steps. Well, if we're starting at 4 on the y-axis and going up another 5.8, we're going to get up to 9.8. And if we're starting at +4 on the y-axis and we're going down 5.8, +4 minus 5.8 gets us a -1.8. So that's where the foci actually are. Okay. Now, back to the front page. I believe that there will be some questions like this on handout 9-8, where I give you some standard form equations and I say, look, don't bother rearranging these, or actually we would call this a general form equation, and I'll say, don't bother rearranging this into a standard form. Just tell me what kind of a shape it's going to be without bothering to rearrange it. And when the numbers in front of the squared terms are the same, what I'm calling here A and what I'm calling here C, when those numbers are the same, then for sure that equation would become a circle. Okay, they can be the same positive or the same negative, although I wouldn't ever make them both negative on you. Okay, when they're not the same, then it could be an ellipse, it could be a hyperbola. If they are the same sign, and again, they don't have to both be positive, they could both be negative. I'm not going to do that to you, okay? But technically, if they are the same sign, so let's say this was a 4 and this was a 9, okay? +4 and a +9. Then for sure this thing represents an ellipse. If one of these is positive and one of them is negative, okay, then for sure it's a hyperbola. Even if they were the same like number, like if this was +3 and that was -3, absolutely going to be a hyperbola, not a circle. Okay, so there's that. All right, that's the notes for 9-8. Again, stay tuned for some more information about graded work upcoming and the calendar for the rest of this year. All right, take care.